Greetings, AP Chemistry students. Today, I want to go through some thermodynamics problems and some calculations with you before I show you one new thing for today. So, we're going to take a look at this question. It's an old one, but it's a good one. It dates back to 2006. And it shows a reaction where carbon monoxide plus half an oxygen makes carbon dioxide. It says determine the value of the standard enthalpy change for the combustion of carbon monoxide using the following information. So we have two reactions and the value for the standard enthalpy changes for those reactions. And what you might notice is that carbon monoxide is a reactant over there and it's a product in this reaction. But if we take this reaction and we reverse it, and we add it to the second reaction, then it will equal the overall reaction because our carbons would cancel out as would half of an oxygen. And if we reverse a reaction, then we change the sign of delta H. And so if we add these together, we would get negative 283.0 kilojoules per mole, meaning this is an exothermic reaction, which makes sense. It's combustion, it would release heat. Then it says determine the value of the standard entropy change for the combustion of carbon monoxide using the information in the following table. So we're going to use the standard entropies of products minus the reactants. So we're going to take the product CO2, which is 213.7, minus the reactants 197.7 plus 1/2 of 205.1. And when we do that math, we should end up with negative 86.5 joules per mole Kelvin. And then it says determine the standard free energy change delta G. Well, delta G equals delta H minus T delta S. Now, the thing to note in this reaction is that delta S is in joules per mole Kelvin and delta H is in kilojoules per mole Kelvin. So we need to convert one to the other. And we're probably going to want to give our answer in kilojoules because delta G is going to be probably fairly large given the value of delta H. So it's going to be negative 283.0 kilojoules per mole minus our temperature is 298 kelvins times negative 0.0865 kilojoules per mole Kelvin. And if you plug that into a calculator, you should get negative 257.2 kilojoules per mole because our kelvins cancel out when we multiply kelvins by something divided by kelvins. All right. Then let's look at some more things it asks. It says, is the reaction spontaneous under standard conditions at 298 kelvins? It would not say spontaneous now, it would say thermodynamically favorable. And we would say yes, because delta G is negative. And then there was another part of this problem, I'm not sure why it's not showing up here, that asked us to calculate the value of K, the equilibrium constant. All right. And we know that delta G is negative 257.2 kilojoules per mole, and delta G equals negative RT ln of K. But the value of R is in joules per mole Kelvin. So we need to convert G into joules so that everything cancels out. So we have negative 257,200 joules per mole equals negative, then 8.314 joules per mole Kelvin times the temperature, we're at 298 kelvins in this problem, times the natural log of K. So to solve this, the natural log of K, we're going to need to divide that out, and we'll find that the natural log of K is equal to uh, 103.8. You'll notice all the units cancel out because our kelvins would cancel with kelvins, and if we divide joules per mole by joules per mole, those cancel out. So then we raise e to both sides, and we get that K equals 1.28 times 10 to the 45th, which is a huge number. It's a very large equilibrium constant, although that should make sense because the value of delta G was quite large and negative. So the whole point of that exercise was to show you that you do need to pay attention to units when you use those equations that seem fairly simple, and they're all on your reference tables. The math is not that hard. You just need to make sure that you're not trying to subtract joules from kilojoules or divide joules by kilojoules. That doesn't work. You either need to have everything in kilojoules, where you would divide by 1,000 to get into kilojoules, or you have everything in joules, you would multiply your kilojoules by 1,000 just to make everything equal. There's one more thing to finish up today before we start the electrochemistry part of this unit tomorrow, and that is coupled reactions. So this is where external sources of energy can be used to force a thermodynamically unfavorable reaction to occur. So, for example, with a cell phone, it is not favorable for that battery to recharge. It's thermodynamically for the reactions in the battery to happen and produce electricity. But you can use some external sources to force that reaction to happen. Or you can use light energy to cause photosynthesis to occur. Or in your body, it uses the conversion of ATP into ADP to drive other unfavorable chemical reactions that keep you alive. So that's coupled reactions. And with that said, that wraps up the first half of this unit on applications of thermodynamics. Tomorrow we'll start with electrochemistry. So y'all have a good one.